Good afternoon. Welcome to today's video. This video will be a little bit on the different side as I really didn't have a lot of time to prepare for it because I came up with an idea and I thought I better get this filmed right away. A few weeks back we covered a time-of-flight sensor. Worked pretty well, accuracy was reasonable, etc. It was a little expensive. But the real problem with it, it took a long time to get readings out of it. And that would have sucked up a lot of our processing time on the PICO. So I've been giving thought to other types of sensors that I can use for detecting objects in the path of the Zoomie while it's traveling along. Basically, a collision avoidance system. Some of you may remember this particular setup that I've got here. It was a test setup for two different purposes. This part was for a different kind of sensor, the time-of-flight sensor. This rig was for testing out the TCRT5000 photoreflective sensor that we're using for the line following functionality of the Zoomie. Putting these two pieces together gave me the idea, or was part of the idea, to test out this sensor, the TCRT5000 photoreflective sensor, to see if we could use that as a proximity sensor. I got everything here I need to do it with, and so what I'm going to do, I will set this box, which will be a stand-in for perhaps another Zoomie, and I will record the sensor readings at a 1/2 inch and then 1 inch increments thereafter. And we can see or get feedback to see if this thing can sense some form of distance. I don't need exact inches or anything like that, or millimeters. I just need some form of feedback that if this is getting within a certain range, bada bing, we might have a collision. So it's very inexpensive. The sensor, I forget what they are off the top of my head, but it's less than $1, I think. Processing time, 25 microseconds. So it's incredibly fast to get a reading and process it. In our case, we really just need to determine a value and make a decision very simply off of that. If it's less than a certain value, we're too close and there's a collision impending. So I'm really kind of excited about this, and I don't know if it's going to work. So let's just go through the process of performing this experiment. I'm going to log it on the screen and in a spreadsheet so we can graph out the results and make a determination. Now, the one thing that we also learned a little bit ago with the color sensor, lighting is going to play a big role in some of this. These different sensors that are working with light or detecting light. So I figure what we'll do, I will run this experiment twice, once with my bench light on and once with the bench light off. From that, I can ascertain if there's a huge difference in the ambient lighting and how it would affect the sensor. For the program, I'm just going to use the same basic code I used for testing out this sensor that we used in an earlier test for the sensor. So let's get started. I'm going to put a 1/2 inch gap here. I think that one's got to be aimed a little better. There we go. And down here on the computer, we'll go ahead and run it. And here's the spreadsheet. These are inches. I won't go back and forth bouncing between inch and metric on this one. It'll kind of take a little too much time duplicating all these readings. So sorry about that. Just follow along with inch, knowing that 1 inch is about 25 millimeters. That should help you out. just looking at the numerical data, the difference between light on and light off wasn't all that great. So the data looks consistent. We can see it here in the graph that the data is fairly consistent between light on and light off. Now, I really don't think I would ever even attempt to differentiate between any decision in this range. See how this is mostly flat or even a shallow curve dropping off? That isn't something that would be enough data or a data point to say, let's make a decision. But right about here is a pretty positive change in value. So that's the start of where I would say we can do accurate sensing. These numbers along the bottom tell us that that is 3 inches away. So from 3 inches to 0, we can somewhat measure the distance using this data. Now again, I don't care about the actual distance as long as I know that at 3 inches, let's go here, at anything below, say, that one's 52.8, this one's 52.4, say, everything below 52.600 is a pending collision. That could be my proximity warning flag. So with that, I'm kind of liking what I see. I think there's actual hope for this sensor to serve in this purpose. Now I can probably try to tweak the resistor values to see if I can get maybe a little linearity out of this. Not that I think it's all that important, but you never know, it might help. Over here, I've got some calculations. Now in this case, let's say our trigger distance is 3 inches. But let's look at this over time, how collision avoidance might work. We know that our motor is going to run at 100 RPM and that the wheel diameter is 1.57 inches. That's that guy right there, and that was checked with a dial caliper. And if you want to know 1.57 inches in metric, really close to 40 millimeters. Sorry I couldn't do that one with the math in my head. But to figure out how our velocity, so to speak, we need to know that in order to understand if we can react quick enough and stop before hitting something. But based on this, using a little math, pi times diameter times the RPMs tells us we're going to be moving at 493.23 inches a minute at maximum velocity in our current configuration. That is 8.22 inches per second. Now, we're looking at a 3-inch warning range. So within 3 inches, I've got to make a decision and stop. If I'm reading this sensor every 100 milliseconds, 10 times a second, 10 hertz, that would give us, if I take this, the time in a second, divided by 10, gives me 0.82 inches. That's less than a third, or less than 30% of that value. Now my goal is to actually be reading this sensor every let's see, I wanted to go with 20 milliseconds, so 20 times a second to be reading this sensor. So that's actually half of that, or 0.41 inches, essentially just a little bit more than a millimeter. Now, this looks very viable for our collision avoidance warning system and control system for that matter. Now, of course, this is all predicated on the idea that there is no deceleration time, where you're moving along at a high velocity and then you got to slowly decelerate. In my testing early on in the early prototypes with this, that isn't an issue. It seems to behave very nicely, starting instantly and stopping instantly. I know there is definitely acceleration and deceleration time in this, but it's very, very minimal. I think I'm really sold on this sensor for our collision avoidance system, or proximity sensor, however you want to look at it. I think, based on the data I'm seeing here, I may try to tweak the readings a little bit, the resistor values specific, to see if I can get the sensor to give me a little different range. And if so, great. If not, I think we're even in the okay range right now. I'm not 100% sold, so I'm going to go ahead with testing one more sensor, and that one I'm waiting for delivery on. They were out of stock when I ordered it. I'm told it'll be here in a couple of weeks, so I will film that story. That one will be another time of flight type of sensor. A little more economical. I'm just hoping I can read it a lot quicker, because it should be able to perform much faster based on the specs that I saw. So at this point, we're moving forward. We've got one possible sensor that should work for collision avoidance, and we've got another one yet coming forward, hopefully in the sequence of filming and so forth. Hopefully that'll be shown in our next episode. Once we get this sensor decided, then I can put together the final touches on our sensor bracket to hold all these different sensors where we need them relative to the road surface and the chassis of the Zoomie. That'll wrap it up for this video. I look forward to seeing you again next week.